This is Joe narrating a PowerPoint in science. It's from the unit on science practices. It's lesson 3, Reason with Scientific Information, found on page 496 in the Kaplan book. So on the science test you will be presented data, charts, and text, and you'll have to take the information in the text or on the graph and draw conclusions from it or predict trends from it. We'll practice that in this lesson. So here's a aerial photograph of Philadelphia, taken from West Philadelphia, looking towards the east. You can see the Comcast Tower and Liberty 1 and the Schuylkill River in the foreground. So this is actually Philadelphia, as far as a photograph can be the actual thing. This is also Philadelphia, and we'd all guess this right away, but this is a map of Philadelphia. So this is just a piece of paper with lines drawn on it, but we can all say that's Philadelphia. You see the Schuylkill River on the left, the Delaware River is on the right. Even a more simple diagram can depict Philadelphia. Here's Philadelphia drawn on the back of a napkin. You see City Hall Square in the middle. Then on the upper right you have Franklin Square, lower right Washington Square, etc. And then you have the Parkway running diagonally from City Hall through Logan Square. So this could also be interpreted as a depiction of Philadelphia. Again, a very simple diagram. You want to capture the essence of Philadelphia in your model and keep it as simple as possible under certain circumstances. In 1953, James Watson on the left and Francis Crick on the right discovered the structure of DNA. DNA is the information-carrying molecule in every cell. Once you understand the structure of a molecule, you can have some idea of how it replicates or reproduces itself and how it works. So the first step was developing a model. They worked with physical models, pieces of metal, to make this model shown in this photograph. So obviously the actual DNA molecule is much smaller than this. It's not made of metal, but this model gets the idea across. A more abstract model in 2 dimensions is this diagram on a 2-dimensional piece of paper, where the blue on either side represents the sugar phosphate structure of the DNA, and the colored shapes in the middle describe the 4 different nucleotides that are in the DNA. So again, this also shows the structure of DNA and gives some idea of how the 2 strands of DNA are tied together. Kids in elementary school will make models of DNA using candy. So they'll have straws and a wire, and they'll thread the candy on the wire to show the structure of DNA. So these can be as simple as you want. The more simple it is, the more detail you lose, but you can capture the essence of many complex scientific ideas with simple models. The word theory in science means something different than it does in everyday speech. So in science, a theory is a well-substantiated explanation of the natural world, meaning it's not just a guess, it's a model of how the world works after studying it for years, doing experiments, and gathering data. In common speech, you might hear someone say, "My theory is this," and really what they really mean is their educated guess is this. But theory in science means something more firm. So predictions in science. Science analyzes nature, it studies nature in order to understand how it works, and then make predictions about what will happen under certain conditions. For example, global climate change. What's going to happen in the future to our world's climate? So science tries to understand nature. Technology, on the other hand, tries to manipulate nature. But to do technology, you need to understand the science. So if we understand the electron movements in semiconductors, and if we understand relativity, we allow development of cell phones and GPS systems, which you use every day. So you have to understand the science to develop the technology, and then to have applications. So here's a diagram, a graph. On the x-axis you see years in 5-year intervals, and on the left, the y-axis, you see the CO2 concentration. ppm means parts per million. For example, in 1975, the CO2 level in these 4 locations was 330 parts per million. So out of every million parts of the air that we breathe, 330 parts of the million were CO2 molecules. The different colored lines on this show 4 different locations: Barrow, Mauna Loa, Samoa, and the South Pole. So they're showing 4 different locations on this one graph, but they all have the same trend. They're going up and down every year, but overall the trend is upward. So we can use graphs like the last one to add correlations. So for example, on the x-axis you have years. Here they're in 4-year intervals, and on the left you have carbon dioxide in parts per million, just like on the last graph. In addition, on this graph we have global temperature anomaly, which means how much the temperature is varying from a previous standard temperature. So as the CO2 level goes up, which is marked by the blue line, the temperature is also going up, marked by the red line. So this is a correlation. It doesn't mean that the rise in temperature is caused by the rise in CO2, but it's something that requires further study because they are definitely correlated. That means as one goes up, the other goes up. And more research can be done to find whether this is a cause-effect relationship or if there's something else causing both of them to rise. So study of nature, gathering data, allows us to make predictions. That's it.